Welcome to lesson 1-2 on the transformations of functions. So we're going to split this section into two parts. So we'll start with example 1, which is on how to translate a function. So we're going to be looking at different types of transformations, and a translation is the first one. Okay, so here's the graph of x squared. That's the blue graph. This is the vertex at the origin. And normally this graph would keep on going, but we're restricting the domain so that it goes from -2 to 2 inclusive. So again, keep in mind for regular f of x equal to x squared, this would keep on going in both directions. Okay, it would have a U shape and not end. The graph of g is obtained from the graph of f with a transformation 3 units down. So how are the equations, the domains, and the ranges of f and g related? So if you look at all the points on the graph of g, which is the red graph, all of the y values are 3 units down from the graph of x squared. So g of x is equal to the original function x squared. Now remember, x squared is what f of x equals, and f of x is a replacement for y, right? So this represents all of the y values. And as I just said, all of them are now 3 less, so we're taking 3 away from x squared. So the equation for g of x is x squared minus 3. If we look at the domains of the function, or the domain is the x values that are included in the graphs. So if we look from left to right, all of the x values from -2 to +2, which is the restricted domain, are the domains for both functions. So that is the same for both. And we use the cornered brackets to show that we're including those values. So again, that's for f of x and g of x. Okay, the range, now we're going to have a difference in range, because remember, range depends upon the y values. So if I look at g of x, right, the lowest point on g of x is down here at -3. So it starts at -3, and we're including that value. And normally we'd say it keeps on going, right? But again, we have this restriction where we cut off the graph where x is -2 and 2. So our highest y value for the g of x graph is at +1. And again, we're including that value. So this is for g of x. The range for f of x, if we look for the lowest point, again, that's at the origin, so that's where y is 0, and it goes up as high as +4, and we include that value. So that's for the original f of x. So this is called a translation. A translation like this one is a particular kind of transformation of a function, one that shifts each point on a graph the same distance and direction. Other kinds of transformations of a function either reflect the graph across an axis or stretch or compress its graph. So we're going to look at both of those things, reflections and stretches and compressions. Okay, so here we have the graph of f of x equal to x squared, and again, same restriction, -2 to 2. So the graph of g is obtained from the graph of f with the translation of 3 units to the right. So how are the equations, domains, and ranges related? Okay, so again, here's our original x squared graph. Here's the graph of g in green. You can see how that vertex went from the origin to the point 3, 0. Okay. So every point on the graph of g is 3 to the right. So f of x becomes x g of x plus 3. So if f of x is equal to g of x plus 3, I can then also say that g of x is equal to f of x minus 3. And this notation means plug x minus 3 into the f function. Well, the f function is x squared. So I'm going to take that quantity, x minus 3, replace the x in the x squared with that quantity, and I end up with the quantity x minus 3 squared. That is the g of x function. So in general, if g of x is equal to f of x minus h, then the graph of g is a horizontal translation of the graph of f by h units. So the thing you need to remember with horizontal shifting is that when this is a difference, it's actually opposite of what you would think. When we have x minus 3 squared, the graph shifts to the right. If we had had another function, I'll call p of x, and let's say it was x plus 4 squared, I'm just making this up, with that being a plus, it would go to the left. So horizontal shift is always opposite of what you would think. Where with vertical shifting, here when this was x squared minus 3, it was exactly what we think, right? Minus 3, we think negative direction, and the graph did drop down by 3 units. So for vertical, if you're adding a constant, the graph moves up. If you're subtracting a constant, it moves down. For horizontal, if you're subtracting, then it moves to the right. If you're adding, it moves to the left. Reflection. So we're reflecting a function across the x or y axis. So we have the graph of a line, 2x minus 6. And the function g, which is a reflection of the graph of f across the x-axis. So how are their equations related? So here's the graph of f. And then what we're going to do, we only need a couple points to graph a line. So if we're flipping over the x-axis, then I can I'll start with this x-intercept, right, 0, negative 6. If I reflect it over the x-axis, then it's going to move up to 0, positive 6. Okay, that's the y-intercept of what will be our new line. We can also reflect this point, they're calling it xy. We're going to flip that over the x-axis, so it's 2 units above, it's going to go 2 units below. Okay, so there's our 2 points that we can use to sketch our line. Okay, so hopefully you can see that reflection over the x-axis. Okay, do you see it? So now to compare the graphs, we know that the slope of the graph of f is positive 2. Right? We look at this line, we're going up 2 and over 1, and up 2 and over 1. Okay? The slope of g is negative 2. We're going down 2 and over 1, or over 1 and down 2, however you want to look at it. So the slopes are opposite, the y-intercepts are opposite, so that gives us the graph of negative 2x plus 6. Okay, this is also the same as saying g of x is equal to the opposite of f of x. So anytime we have a function where, let's say if I have f of x equal to negative x squared, that means that this would be the graph of x squared flipped over the y-axis. So it would look like a downward opening parabola. Okay, so g of x for our line is equal to the opposite of f of x, and f of x was this original line, 2x minus 6, and when I distribute that negative, I get negative 2x plus 6 And that's exactly what we have here. Okay. Now this time we're going to take the same line and reflect it over the y-axis. So if we start with the x-intercept, we have an x-intercept at 3, 0. It's going to reflect across the y to negative 3, 0. And then again, we can choose any point. If I take this point here, x comma y, looks like it's 4 over and 2 up. So now it's going to be 4 in this direction and 2 up. The y-intercept isn't going to move, right? It's on our line of reflection, so it stays there. So I actually didn't need a second point because I already had that one. So there's my line. So hopefully again you can see that symmetry, okay, over the y-axis of the two lines. So the slope of f again is 2 over 1. The slope of this graph is negative 2, but the big difference here is the y-intercept is still negative 6. So that gives us this equation, h of x equal to negative 2x minus 6. So the function h of x has a slope that's the opposite of f of x, but the same y-intercept. This is also the same as looking at the notation this way, that h of x is equal to f of negative x, which means I take the function, the original function, 2x minus 6, and I replace the x with a negative x. 2 times negative x is negative 2x minus 6, and that gives me my new function. So when you have a reflection over the y-axis, you put the negative inside the function. You replace every x in the function with a negative x. When you're reflecting over the x-axis, that's when we put the negative in front of the entire function, right? Surround it with parentheses and distribute that negative over every term. Stretches and compressions. So here we're going to look at the absolute value of x. That's the V-shaped graph you see here in blue. And again, the domain has been restricted. Normally this would keep on going without end, but we're stopping at negative 4 to 4. G of x is this function, and g of x is equal to 2 times f of x. So how are the domains and ranges related? Okay, so 2 times f of x is the same as saying g of x is equal to 2 absolute value of x. So you can see visually how the graph changed. Let's actually look at the coordinates. So we have all the points, well, we skipped over some, negative 4 to 4, but we have negative 2, 0, 2, 4. The y values that go along with that graph, again, this is from the blue graph, so at negative 4 we have 4, negative 2 we have 2, 0, 2, and 4. For g of x, what we're going to do is take this column, all of the values of f of x, the y values, and multiply by 2. So when x is negative 4, for g of x, the y value becomes 8. When x is negative 2, normally for the original function, we have a value of 2. We're doubling that, so it becomes 4. When x is 0, that's not going to change, right? 2 times 0 is still 0. And then for the other two coordinates, we have 2 times 2 again, right, which brings us up to 4, and 2 times the 4, which brings us up to 8. So the domain of f and g are the same, right, just like the parabola that we looked at before. The y values are all multiplied by 2, so the function with the So for the function with the given domain, the range of f, 0, 4, is doubled for g, and that becomes 0, 8. Okay, we have a new higher value for y's of 8. So a transformation that increases the distance between the points of a graph and a given line by the same factor is called a stretch. So this is a vertical stretch, okay, by a factor of 2. Again, we're going to use absolute value of x, and now we're going to look at what happens when we do f of 2x. So this function g, or h rather, would look like this, absolute value of 2x, because we're plugging the 2x into this x. We're replacing this x with the 2x. So let's see what happens here. Again, the domain of the original function is restricted from -4 to 4. Now this time, this is a little more complicated. Notice we went from -2 to 2 with the x values. Okay, here's the y values, same as before. For h, though, this is going to be a little different. What we're doing here is we're finding f of 2x. So x in the first line is -2. So 2 times that becomes f of -4. F of -4 means what is the y value from the original graph when x is -4, and that's 4. For the next one, we're plugging in -1. So that means h of 2 times -1, which is f of -2. F of -2 I can get from the chart here, or I can go to where x is -2 on the graph and get it from here. Either way, I get a y value of 2. And again, this last column are the y values for the h function. When I plug in 0, again, there's no change. When I plug in 1, I'm doing 2 times 1, so it's really f of 2, and f of 2 is equal to 2. And for the last one, f of 2 times 2, okay, is really f of 4. And if we look at the original graph where x is 4, the y value is 4. So for each corresponding output, the value of the input for h is half the value of the input for f. The two functions have the same range, but the values in the domain of h go from -2 to 2 inclusive, and they are half as large as the values in the domain of f, which was from -4 to 4. So right there you can see how these x values are limited from -2 to 2, where these were restricted from -4 to 4. So a transformation that decreases the distance between the points of a graph and the given line by the same factor is called a compression. So this is a horizontal compression. H is a horizontal compression of the graph of f by a factor of 2. So to summarize, for stretches and compressions, so again, vertical, if you have a value of a that is greater than 1, so a is the value that in this case we were calling this 2 is a. Okay, so when you have a 2 in front of your function, if I had a 2x squared or a 2x cubed, okay, that 2 doubles all the y values. So it's going to be a vertical stretch. If the value of a is between 0 and 1, then think about it this way. For instance, if this were a half, I'm taking half of all the y values, so I'm not making them larger, I'm making them smaller. That would actually bring the y values down, right? And we call that a vertical compression. So greater than 1, vertical stretch. Between 0 and 1, it's a vertical compression. Horizontal, again, is opposite. So when a is greater than 1, like you saw in our last example, here a is 2, and we had a horizontal compression. If the value of a is between 0 and 1, okay, or think of it as 1 over a, then it's going to stretch horizontally. So that completes part 1 of lesson 1.2. We'll pick up with part 2 for the next class.